welcome to True Projects. In this video, we are going to explain about the project entitled as Attention Enhanced InceptionNeXt based hybrid deep learning model for lung cancer detection. So before getting into the video, let me give you the brief description about the project. The title refers to a deep learning approach that uses the InceptionNeXt architecture to extract complex features from lung images. The attention mechanism enhances the model's ability to focus on critical regions like nodules or abnormal tissues, improving detection accuracy. Being a hybrid model, it combines multiple deep learning strategies to achieve better sensitivity and reliability in identifying lung cancer from CT scans or X rays. This approach aims to support early and precise diagnosis, reducing the risk of missed cases. Coming to the abstract describes a deep learning based approach for detecting lung cancer using medical imaging data like CT scans and X rays. It emphasized that lung cancer is often fatal because it is diagnosed late, making early detection vital for improving survival rates. The proposed method uses a hybrid model that combines the InceptionNeXt architecture for efficient feature extraction with an attenuation mechanism that highlights the most important areas in the images, such as potential tumors or abnormal tissues. This combination allows the model to detect subtle patterns that might be missed by traditional methods. Overall, the approach aims to improve accuracy, reduce false negatives, and serve as a support tool for radiologists, helping them make faster and more reliable diagnosis. Coming to the existing system for lung cancer detection mainly relies on manual interpretation of medical images by radiologists and convolutional image techniques, which can be time consuming and prone to human error. While traditional machine learning methods such as support vector machines, random forest, and basic convolutional neural networks have been applied to classify lung images, they often face challenges in extracting complex features and capturing spatial relationship within the images. Additionally, CNN-based models without an attenuation mechanism may fail to detect subtle abnormalities, resulting in lower sensitivity and higher false negative rates, which limits their reliability in early lung cancer diagnosis. Coming to the proposed system or base paper work, the proposed system is a hybrid deep learning model that integrates the InceptionNeXt architecture with an attenuation mechanism to enhance lung cancer detection. InceptionNeXt allows the model to perform multi-scale feature extraction, capturing both global and local patterns in lung image effectively. The attenuation model helps the model focus on the important region such as nodules or abnormal tissues, while ignoring irrelevant areas, improving detection of subtle abnormalities. This combination not only boosts classification, accuracy, and sensitivity, but also provides interpretable visualization to assist radiologists in clinical decisions. Overall, the proposed system is designed to deliver faster, more accurate, and reliable early lung cancer diagnosis compared to existing methods. Coming to the data sets, we have used two different data sets. Among them, the first data set is IQOTHNCCD lung cancer data set. The data set is publicly available collection of thyroid CT scan images specially designed for research in automated lung cancer detection. The images are categorized into three classes: normal, benign, and malignant. With annotations provided by experienced radiologists to ensure accurate ground truth labels. The dataset contains approximate about 1097 to 1197 CT scan images with a large number of malignant and normal cases compared to benign class. It is widely used in machine learning and deep learning research, enabling models to learn key factors for early and accurate detection of lung cancer, supporting the development of AI based diagnosis tools. The second dataset is chest CT scan images dataset. The dataset contains annotated CT scan images of the chest for lung cancer detection and classification. The images are labeled across four categories: enabling models to distinguish between different cancer subtypes and healthy lungs. The dataset is organized to support training, validation, and testing of deep learning models and contain approximate 748 images in total. It is suitable for multi-class classification tasks, allowing CNNs and other deep learning architectures to learn discriminative features for accurate and early lung cancer detection. Coming to the novelty or extension or enhancement or improvement. As an extension to the main model, the YOLO family of object detection models has been applied to identify and localize abnormalities in lung images. YOLO enables real time detection by predicting bounding boxes around regions of interest, such as nodules or tumors, allowing the system not only to classify the image but also to pinpoint the exact locations of potential cancerous regions for more precise analysis. Furthermore, to make the model's prediction more interpretable, explainable AI techniques like GradCam are used. GradCam generates heat maps that highlights the areas of the images most influential in the model's decision-making process. This helps radiologists and users understand why the model made a certain prediction, increasing trust in AI assisted diagnosis and providing visual insights into critical regions like tumor or lesions. Along with that, to make the system user friendly, a Flask web framework is used to build a simple UI. This interface allows users to upload lung images and receive predictions from the trained deep learning models. By connecting the backend model with a web based frontend, users can interact with the system easily, enabling practical deployment for real world use cases like clinical decision support. Coming to the flow of the work, first we need to import the packages. The first step involves importing all the necessary Python libraries and frameworks required for the project. This includes PyTorch and Torch Vision for deep learning, YOLO frameworks for object detection, OpenCV for image processing, and Flask for building the web application. Additionally, utilities for data handling, visualization, and model evaluation are imported to streamline the workflow and ensures efficient training and interference. Proper package setup is critical for seamless integration of classification, detection, and web deployment stages. Next, data preparation. The project uses two major data sets. One is IQOTHNCCD lung cancer dataset, which contains CT scan images categorized into normal, benign, and malignant, and the chest CT scan image datasets, which contain multiple cancer types and normal scans. Images from both datasets are loaded and organized, ensuring that labels are correctly associated with each image. This step is critical for both classification and detection tasks as it ensures the model is learning from accurate and well structured data. And next, we have pre processing. The classification image undergoes data augmentation to enhance model generalization. This includes resizing to 299 into 299 pixel, random horizontal flip, random affine transformations, and conversions to tensor format. For detection, the datasets are merged into a single dataset and a data.yaml file is created to specify image path and class names for YOLO models. Pre-processing ensures that images are in a uniform format suitable for both deep learning classification and object detection. Next, dataset preparation. After pre-processing, the image file paths are loaded and the defined transformations are applied. The dataset is then split into training, validation, and testing sets using the split function to maintain the class distribution across all subsets. The step is essential for fair evaluation of the model and to prevent bias during training, ensuring that the models perform reliable on unseen data. Next, maintain parallel dataset. Two separate datasets are maintained for the two tasks. For classification, each image is paired with its class label. For detection, each image is paired with bounding boxes annotations indicating the local of abnormalities. Maintaining this parallel dataset allows the workflow to train models simultaneously for both classification and detection tasks without interference. Next, model training. Classification branch multiple baseline models like ResNet 50, DenseNet 169, EfficientNet V2 Convolutional next, Inception Next, and transformer based models such as Swin Base, Maximum Wit, and DEIT3 are trained to provide a performance benchmark. The proposed model is a light-weighted hybrid CNN WIT model enhanced with Inception Next and attenuation mechanisms to capture both local and global features effectively, improving accuracy and sensitivity. For YOLO based detection branch, YOLO models are trained to detect abnormalities in lung images by predicting bounding boxes and their corresponding classes. Evaluation metrics including MAP, precision, and recall, which helps compare YOLO versions and select the best performing model for detection. Next, interference pipeline. The trained models are integrated into an interference pipeline using Flask. Users can upload the image, which first goes to the YOLO model for detection of abnormal regions. The detected regions are then fed into the classification model to determine the specific type of lung cancer. The pipeline ensures efficient and accurate predictions in real time, bridging the gap between model deployment and practical usage. Coming to the Flask, a Flask based web application provides a user friendly interface for uploading images. On the backend, YOLO performs detection and localization of abnormalities followed by classification using the best performing model. The front end displays results including bounding boxes around detection regions, predicted cancer class, and confidence scores. This makes the system accessible for clinicians or users, allowing them to visualize and interpret predictions easily. The algorithms used are baseline models, ResNet 50, DenseNet 169, EfficientNet V2 medium, convolutional next base, Inception next base, mobile width small, con width base, swim base, maximum width base, DIT3 base, and proposed models we have used lightweight hybrid CNN width model, enhanced with Inception next, grid attenuation, and block attenuation mechanisms. And as an extension, we have used YOLO like YOLO V5, YOLO V8, YOLO V9, and YOLO V11. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of application framework Anaconda, primary language Python, front-end framework Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python, that handle server side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Models. These are the model files which contain the algorithm information which will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, first you need to copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. Now, the home page of the project has been displayed in the browser. This is a front-end built using Flask framework. In this page, we have home button and sign up button. Firstly, click on sign up button so that the create account form will be opened where you need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on create an account so that all the given details are stored in signup.db and login.html will be open where you need to access the application with username and password. Then click on sign in so that the prediction page has been displayed. In this we have home button, prediction button, graphs button, notebooks button and sign out button. Firstly click on prediction button. So as we are using classification and detection for two different as we are using classification and detection for two different data sets along with extinction as YOLO. Now let us check one by one. For first data set of test CT scan, the upload CT scan form will be open where you need to upload the image and then analyze the image. Choose the file, click on analyze image so that the given image is pre-processed and the output is displayed like the analysis has been completed. This is the original image and this is a GradCam image. And the available classes are given here and class type is also given. The classification result like predicted class is adenocarcinoma. The confidence score is 100%. We also have the available classification classes, recommendations and safety precautions, and important notice. Now let us click on upload another CT scan. Again, the form will be opened. You can choose. The image has been successfully uploaded. Click on analyze image so that the given image is pre-processed and the output will be displayed like the available classes is large cell carcinoma. Analysis is completed. This is the original image which we have uploaded and this is a GradCam visualization. We also have the classification results like the predicted class is large cell carcinoma and confidence score is of 100%. We also have available classification classes and recommendations and safety precautions. In the same way, click on upload another CT scan image. The form will be open where you need to choose the image. The image has been successfully uploaded. Click on analyze image so that the given image is pre-processed and the output will be displayed as normal, which means the analysis completed. This is the original image which we have uploaded. This is a GradCam visualization. The classification results are normal. The confidence score is of 0.99 percentage. And we also have the available classification class like normal is selected and recommendations and safety precautions. Click on upload another CT scan image so that the upload CT scan image form will be opened where you need to choose an other image. The image has been successfully uploaded. Click on analyze other image so that the given input is pre-processed and the output will be displayed as squamous cell carcinoma. The analysis is completed. This is the original image. This is a GradCam visualization. And the classification result predicted class will be squamous cell carcinoma. The confidence score is of 0.99 percentage. The available classification class is selected. And we also have the recommendations and safety precautions. So now let us check with the other data set that is IQOTHNCCD so that the upload medical image form will be opened for IQOTHNCCD dataset. Now let us check for this by choosing the files like images. The image has been successfully uploaded. Click on analyze image so that the given image is pre-processed The output is defined as benign class. The analysis has been completed. This is the original image and this is a GradCam visualization. And we also have the predicted class is benign class. Confidence level is 100% and benign case has been selected. We also have the recommendation safety precautions. Now click on upload another image so that the form will be opened again where you need to enter the other image. The other image has been successfully uploaded. Click on Analyze Image so that the given image is pre-processed and the output will be displayed as malignant case. The analysis has been completed. This is the original image and this is a GradCam visualization. The classification results are given below, like the predicted class is malignant case and the confidence score is of 0.9997%. The available classification class malignant case has been selected. We also have the recommendation and safety precautions and click on upload another image so that the upload medical image form will be opened. You need to choose the image. The image has been successfully uploaded. Click on analyze image so that the given input image has been pre-processed and the output will be displayed as normal case. The analysis has been completed. This is the original image and this is a grad cam visualization image. And the classification results, predicted class is normal case and confidence score is of 0.9898%. And we also have the available classification classes like normal case. We also have the recommendations and safety precautions. And now let us check with YOLO detection. When you click on YOLO detection, the upload medical image will be open where you need to select the medical image file for YOLO detection analysis. Now click on choose the file. Click on analyze image so that the given image is pre-processed and the output has been detected with the bounding boxes. Like the detection information, the YOLO has been detected. The localization is of bounding boxes. The detection features are given below. Now click on graphs so that the classification and detection graphs will be open. Let us check one by one. First, we have chest CT graphs. In this, first, we have confusion matrix graph. This confusion matrix shows how well the efficient net model classified four lung tissue types. More predictions lies on diagonal, indicating high accuracy with only a few misclassifications between similar classes. Overall, the model performs very well across all categories. Next, we have accuracy graph. This bar chart compares the classification accuracy of different deep learning models. Most models achieve very high accuracy with the proposed hybrid model, and several CNN and transformer based models perform the best. Maximum width base shows comparatively lower accuracy among the evaluated models. Next, we have precision by model graph. This bar chart shows the precision achieved by different machine learning models. Most models demonstrate consistently high precision, indicating lower false positive rates. The proposed hybrid and transformer based model rank among the top performers. Next, we have recall by model graph. The bar chart compares recall scores across different models, showing the most model achieve very high recall. The proposed hybrid model performs competitively with top CNN and transformer based models, while swim based and maximum bit based show slightly lower recall than the rest. Next, we have F1 score by model graph. The graph shows F1 scores of different ML models, with most models achieving strong and closely clustered performance near 0.98% to 0.99%. The proposed hybrid model performs on par with established CNNs and transformers, while swim based and maximum bit based exhibit slightly lower F1 scores compared to the top performing model. Let us check with another data set. In this data set, first we have confusion matrix graph. The confusion matrix shows that Con-bit-based correctly classifies most samples with perfect detection of malignant cases and strong performance on normal cases. A few benign cases are misclassified as normal, indicating minor confusion mainly between benign and normal class. Next, we have accuracy by model graph. The bar chart compares classification accuracy across different ML models. The proposed hybrid model achieves the highest accuracy, while Sven based shows the lowest performance. Overall, most models perform strongly with accuracies clustered close to 95 to 99%. Next, we have precision by model graph. The graph shows precision scores for different machine learning models. The proposed hybrid model achieves the highest precision, while Swin based has the lowest. Most models maintain high precision, indicating reliable positive predictions across architectures. Next, we have recall by model graph. The graph compares recall values across different machine learning models. ConNeXt based and the proposed hybrid model achieves the highest recall, indicating better detection for true positives. Swen based and maximum bit based shows comparatively lower recall, missing more positive cases. Next, we have F1 score by model graph. The bar chart compares F1 scores of different ML models, showing that the proposed hybrid model achieves the highest performance, closely followed by CNN based models like ConNeXt and EfficientNet. Transformer based models such as Spin based perform comparatively lower, indicating the hybrid or CNN approaches are more effective for this task. And now let us check with detection graphs. In this first, we have YOLO precision graph. The graph compares precision across YOLO versions, showing that YOLO V8 achieves the highest precision, followed closely by YOLO V9. In contrast, YOLO V11 has significantly lower precision, indicating more false positive compared to earlier versions. Next, we have YOLO recall graph. The graph shows recall performance across YOLO models with YOLO V5 and YOLO V8 achieving the highest recall, meaning they detect more true pos objects. YOLO V9 and YOLO V11 have lower recall, indicating a higher chance of missed detections. Next, we have YOLO MAP graph. The bar chart compares mean average precision across YOLO versions. YOLO V5 and YOLO V8 perform best with the highest MAP. YOLO V9 is slightly lower and YOLO V11 shows the lowest performance. And then click on sign out. So finally, the project effectively improves lung cancer detection by focusing on critical areas in medical images. It achieves higher accuracy and reliability compared to traditional methods, enabling early and precise diagnosis. This approach shows strong potential for supporting clinical decision making and improving patients' outcome. So this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.